Hey guys, this is Physics Tutor here, and today we're going to learn a little bit more about the Schrodinger equation. The Schrodinger equation is pretty much like the analog of F equals ma, and what we're going to do today is we're going to learn how to get it and like derive it pretty much, and then we're going to learn how to solve it, because there's no point deriving this big hunking thing if you don't know what to do with it. So before we even start, let's get familiarized with some of the terminology that I might be using. So you guys should know what a Hamiltonian is. That's called a Hamiltonian, and you guys should probably have a clue of what that is by now. I'm sorry, you guys can't see that. There you go, Hamiltonian. So part of my messy handwriting. You guys might have a clue of what that is by now, but it's pretty much it's an operator. So you take it and you apply it to something. So it's like the operator, like plus, minus, multiplication sign, whatever, and you apply it to something. So when you apply to something, all you do is you pretty much take the wave function of it. So what we're gonna do is we're gonna apply the Hamiltonian to our energy. Now that E is the energy, right? The total energy. So when you and that is equal to your kinetic energy plus your potential energy. Now when you apply the Hamiltonian to it, you pretty much all you do is you take the wave function x comma t, right? And if I forget to write that, just pardon me, but I'm pretty much referring to it as being x comma t. Okay. That's a t, x comma t, yeah. So with respect to position and time. So that's where we'll be. Okay, so let's play around with this a little bit. We know that energy is equal to h bar omega, right? H bar omega times psi of x comma t. That's what you call psi is equal to. Now we know kinetic energy is p squared over 2m, or at least you guys should have a clue for that by now. And we should also know that momentum, which is p, is actually h bar k. So our kinetic energy would come out to being h bar squared k squared over 2m, then our x comma t plus v of psi of x comma t. Now you might be thinking, whoa, this got out of hand really quickly, but it's not a lot. I mean, the h bar is pretty much the reduced Planck constant. That's straightforward. That's just the omega. We all know what that is. Omega. K, we know that. We all know that is. And m is a mass. It didn't get out of hand yet, and I'm not trying to scare you or anything after that. But so we'll just put that away for a second, and we'll just go on this second topic, which I want to cover with you, just for a second. One sec. Not important. Okay. So what we're gonna do is we're gonna start taking we know that according to Euler's theorem, I'm pretty sure that's what it's called. I'm not like 100% sure, but that is what the e to the I kx minus omega t. That is what the wave function is defined as being, right? Now, what we do is we're gonna start taking derivatives of this thing, partial derivatives, straight off the bat. So for the first one, let's take the partial derivative, and now I'm gonna write it as this notation, psi of xx. That just means that it's the second partial derivative of this thing. Excuse me. So let's just start taking them right off the bat. So we know that psi of xx, which is pretty much d squared psi over dx squared. And if you don't want to do the math, you can just trust me on this one. Negative k squared, and then you're gonna get the same thing back. So I'm just gonna say that's psi of x comma t. And similarly, that's the second derivative of with respect to space, and we're gonna take the second derivative with respect to time. And that's the notation for it that I'm gonna use just for simplicity. I mean, I know that there's other notations, and we're gonna get negative I comma and then omega, and then we're gonna get psi again. Okay, which is actually x comma t. Good. Okay. So you might be asking, okay, so what do we do with this thing now? Well, what we're gonna do is we're gonna make this. We're gonna play around with it, and what we want to do is we want to make it look like something like this and something like that, so that we can actually sub it in, right? So let's start right off the bat. Let's say, well, okay, let's isolate for the wave function right now. Okay, so we get that. Okay, let's work with this one. We get that psi of xx over negative k squared is equal to x comma t, and all I did is I moved that negative k squared over, right? That's a k squared, and that's all I did. Now what we do is let's multiply both sides by h squared k squared over 2m. So h squared k squared over 2m psi of xx over negative k squared, that's a multiplication, is equal to h squared, I'm sorry, that's h bar squared, sorry, k squared over let's see, 2m multiplied by this thing right there. Alright, and now we quickly figure out that we can cancel some stuff out. We can say this counts right there, this counts right there, and that's just going to be a negative sign right there. So we know that negative h bar squared over 2m times psi of xx is equal to h bar squared k squared over 2m times psi of x comma t. And look at what we've just done. Look at what we've just done. We've pretty much gotten this thing right there, right? That thing is that thing, and we can sub that in. I'm not gonna sub it in yet. What I want to do is I want to play around with this one again, and I want to see if I can get something similar to that. Sorry. So I'm just gonna get another piece of paper, and you guys can jot that down if you want, or just trust me on this one. Okay, so what we had pretty much was psi of t is equal to negative I omega psi of x comma t. That's a x and comma t over there. Sorry, you guys can't see this. Yeah, maybe that's a little bit better. Okay, and we're gonna try and do the same thing. We're gonna try and get it to look the same as something in the previous thing we had. So let's just isolate for the wave function like we did last time, over negative I omega is equal to psi of x comma t. And all I did is I pretty much just moved that over there, right? That's not much of a difference. Okay, so now I want you guys to notice something. If you had I is pretty much a root of negative 1, right? That's your imaginary unit. So say you had 1 over root of negative 1. If you multiply top and bottom by root of negative 1, you would get root of negative 1, and these two would just cancel out to become negative 1, and you would pretty much get negative root of negative 1, which is just negative I, right? You guys understand that? Okay, I'm gonna do the same thing over here. So I'm just gonna move the I up, and notice that there's gonna be a sign change. So it's gonna be psi that's a psi of t, sorry, psi of t times I, and I'm gonna move that w back, omega back over, and I'm gonna get omega. Now what I'm gonna do is I'm gonna multiply both sides by h bar. Alright, h bar. Now watch what we just did. Isn't that the same thing as that over there? Sorry, the first thing that we got when we got it, isn't this the same thing as this? Right? So now we can start subbing stuff in, and we pretty much understood. Okay, so let's just sub that in right there. So we get I h bar, and now remember how I said that was a derivative? Well, I'm just gonna write in derivative form, so that is actually easier for us to see. So d of, that's partial derivative like I said, over dt is equal to, now remember how we got the other one? I'm just gonna sub that one in. I'm just gonna move it down here so you guys can actually see what it is. See that? I'm just gonna sub it in right there, this part, negative h bar squared over 2m, and similarly I'm just gonna write that as its normal partial derivative form, psi of squared, and I'm just gonna leave that as there as v psi of x comma t. And lo and behold, that, my friends, is the Schrodinger equation.